everyone. It's great to see you all over here for the workshops. We're starting off with Ben Bakker from UIC, who's going to be talking about Baily Borel Compactification of period images and the b-semiampleness conjecture.
Great, thank you so much. Thanks for the introduction and for the invitation, although I'm just coming 3 minutes away. So I guess thanks to everyone else who traveled further, especially, it's kind of crummy weather. Before I begin, let me say this is all joint with Filipazzi, Mauri, and Tsimerman. We also apologize, so this title is very long. So really, because I want to emphasize more sort of how ordinality enters into the picture, so it's in keeping with the theme, I'll probably not say so much about the proof of the b-semiampleness part, although I will say a few words at some point. Okay, so I want to start recalling sort of a classical story. The classical story being about sort of the moduli space of principally polarized abelian varieties, which sort of starts off life as a complex analytic variety, which is the quotient of the Siegel upper half space by the action of FB2GZ. Okay. I want to start with some work of Satake in '56, who sort of motivated by sort of understanding some ideas coming from reduction theory, introduced a topological compactification of this space, which is given by, call it SPP. It's given by adding the sort of AGs for lower G. Okay, so sort of the open part is this space, this quotient that I already mentioned. And then into the boundary, we add in sort of AG minus 1, and then so on and so forth, all the way down to A1, which is the modular curve, and then A0, which is a point. And also he suggested that sort of this topological space should also be the topological space underlying an complex analytic variety. So this was then realized by Baily a couple of years later, who actually did slightly better, who showed that this topological compactification underlies a complex projective variety, which is compatible with that analytic structure. Okay, so he showed that this space is proj of a certain graded ring of automorphic forms. Okay, so somehow this space starts off life as a complex analytic variety, but in particular now you know that sort of this open part has an algebraic structure. I should say, I'm sure there's many people here who can correct my history, so please do so, because I'm doing my best to try to track down the references. Now this, as you may know, this algebraic variety is quite singular at the boundary. Too singular, in fact, to support sort of a universal family of degenerating abelian varieties, but it still has a sort of modular interpretation. Which I couldn't pin down a precise reference. It was certainly known sort of in the 70s, the Mumford and others, and it certainly appears eventually in print in Falting's Chai. But basically the point is the following. So I want to consider families of abelian varieties, one parameter family, so over algebraic curves. So let Z naught over C, I mean Z upper 0, Z circle over C circle be a family of abelian varieties. And I want to consider sort of a 1-point partial compactification of the curve where I want to take the limit. So let's say that point is 0. And I can take this family and I can look at the neuron model over this curve, and it has a special fiber. Z0. And up to possibly going to a finite cover so that this abelian variety has semi-stable reduction. This Z0 will be sort of a finite extension of a semi-abelian variety. Let's say Z0 is the semi-stable neuron model fiber. Which, like I said, is an extension of a semi-abelian variety by a finite group. In particular, the semi-abelian part is the extension of a compact abelian variety by a torus. And so that compact abelian variety is the limit point. I mean, it's some smaller dimensional compact abelian variety, and that is the limit point in this topological compactification. So compact part equals limit. So like I said, there's no universal family, but sort of for one parameter degenerations, there's a moduli interpretation of these points we're adding to the boundary. This is already implicit in point 2. But there's a natural polarization on this projective variety, which has a geometric interpretation. Polarization. Namely, if I take the universal family of abelian varieties, I'm going to write a curly AJ here, because really it's the universal family lives on the stack and not on sort of this core space. I only apologize that my family is D, which is terrible, but I need X and Y for later. So somehow those letters need to be reserved. So this is my universal family of abelian varieties. There's a natural line bundle, which I'll call like this, which is just the determinant of the push forward of the relative one forms. This line bundle has positivity properties. And in fact, these automorphic forms that I mentioned over here are sections of this line bundle. And this compactification is such that this line bundle extends to an ample. Extends to ample line bundle, which I'll denote like this. Okay, so let me also make a slight note here, which is that usually whenever I am talking about line bundles, I'm always going to mean up to taking a power, just to kind of get around the kind of difference between the stacky space, the script A and the non-script A. I want to pass these things with them. Okay, so this is really up to a power. Okay, and finally, so I said over here that there's no universal family, but there's still a universal property that this algebraic variety satisfies. Which is sort of, in some sense, it kind of has a universal family, at least with respect to families of abelian varieties over the complement of a log smooth divisor. So this was observed by Borel in 72, and the statement is roughly as follows: if X comma D is log smooth, so X is smooth and D is a log smooth divisor. Suppose I
couldn't have log smooth.
Sorry?
Borel didn't have the concept of log smooth.
Well, by log smooth, okay, yeah. So I'm using that as a shorthand for X is smooth and D is a log smooth divisor, which.
She also didn't have it.
Well, okay, so, okay. Well, I'll say what he actually talks about in a second. But yeah, let me keep that for the moment. I mean, this statement was formulated for sort of polydisks, and that's going to be 5 prime. And the statement is, so suppose you have an actual family on the complement of this log smooth divisor, which I'll call X circle in keeping with the notation over there. So an actual family of abelian varieties means I have a map to the stack. And that maps to this compactification. And the statement is simple, it's just that this map from the complement of D extends over the divisor. So this F, so there exists, maybe I'll call it an F bar. And moreover, this extension is compatible with this natural line bundle. Okay, so what do I mean by that? Well, on the one hand, you can sort of pull back this ample extension of the line bundle here. And on the other hand, there is a natural extension of the line bundle you would form, the line bundle you would form from the family as up here, either given by Hodge theory, or if you like, involves taking possibly up to a cover a semi-stable model and taking the determinant of the push forward of the log differentials. Okay, so either way, there's sort of a natural way to extend the line bundle here. I'll call that L sub X. The notation I'll typically be using. So this is the natural extension of this line bundle you form on X minus D from the family. And the statement is just that the sort of natural Hodge theoretic extension of the line bundle agrees with the one pulled back from this compactification. Okay, and this is related to, in fact, stronger than this is what Borel actually proves, which is this same statement in the analytic category where X comma D is a polydisk with boundary, some union of coordinate hyperplanes. Okay, so even analytically, for X comma D equal to polydisk of coordinate hyperplanes.
So can I ask, because
Yeah, please.
I apologize, I don't see very well. So the compactification of H part is which one you wrote, because you wrote a line bundle on it?
Yes.
And which extension you have? What is the extension of AG you take here? Is that small one you had at the very beginning?
Yeah.
This is the same. This is the same compactification throughout. So yeah, this is the one I talked about over there. This
Yeah, okay.
Satake and Baily Borel
Yeah.
compactification.
And then you said that you extend a normal crossing compactification,
Yes,
and it maps to the very singular compactification. of
Correct.
AG.
yes,
And then you say that the line bundle on AG pulls back to the one which is given by the one forms. Okay.
correct. Yes, yeah. So geometrically given by the log one forms in the sort of semi-stable case, or in general, sort of given again up to a power from the sort of natural Hodge theoretic extension. The up to a power is also important here, basically to kill off the quasi and the quasi-unipotent monodromy that might show up. Okay, but I'm going to sweep that under the rug. Other questions? Yeah.
So the one given by the differential form construction is that's an extension of the thing without a power, right?
That's an yes, yeah. So once you up to the finite cover, you have a semi-stable model, then there is no power. But to get that to agree with the one that's actually pulled back, like in order for it to descend, basically have to take some power to kill off the roots of unity that show up. Does that make sense? Okay, cool. Okay, so everything I said here was for AG. This was shortly thereafter generalized to other arithmetic locally symmetric varieties. So first done topologically by Satake in 60, and then by Baily and Borel in 66. This was done for same for producing a compactification, which is usually called the Baily Borel compactification of an arithmetic locally symmetric S. Of any arithmetic locally symmetric S. Okay, great. Okay, so around or around the same time or shortly, shortly after this, sort of the.
But they really use the arithmetic aspect, although of course all the groups are arithmetic in higher rank.
Did they use the, yeah, I think especially here, I don't.
Just for the cusps or what?
Yeah, for sure. I think maybe even Satake also used the arithmetic conditions actually, right? So that's the cusps. Yes, that's right. The sort of theory of variations of Hodge structures and period maps was being developed roughly at the same time by Griffiths. I mean, by many people, but Griffiths and Lean. So let me talk a little bit about this. That kind of paints, in some sense, a similar picture for any smooth projective varieties. So again, let's take x comma d to be log smooth, just for simplicity. And I want to consider smooth projective families over the complement. Smooth projective. And I want to look at the local system that's sort of fiber-wise computing the kth cohomology of the fibers of this family. Like this. Again, I apologize for this notation. C sub Z. And this local system comes equipped with a variation of Hodge structures. Which means a lot, but at the very least, it means that there is a filtration on the associated flat vector bundle. Okay, so I at least want to record that data. So there's some holomorphically varying filtration f dot b of the associated flat vector bundle, which is just this local system tensor analytic functions. That satisfies some properties. But given this filtration on a vector bundle that has a flat connection, you can then sort of look at the coordinates of the filtration with respect to a flat frame, and that gives you a period map. Okay, so that gives a period map, a holomorphic period map from sort of x naught analytified to a flag variety that gives you all filtrations of a certain type on the frame vector space, modulo the action of monodrome, which I'll just call gamma at the moment. So you get some analytic map called the period map to a period domain parametrizing the filtrations, again, modulo the action of monodromy of the local system. And in fact, okay, so this analytic map, Griffiths showed, if you take its image, which a priori could be some mess, actually, if you take its closure, it's a complex analytic subvariety of D mod gamma. Let me call that curly Y. So you get some factorization like this. And sort of he asked several questions. 70. So first of all, is this curly Y algebraic? Okay, curly Y algebraic. Second, well, there's once again a natural line bundle floating around, which for curvature reasons sort of has a definite curvature form. You expect it, if it were algebraic, to be ample. Okay, so that's called the Griffiths bundle. So it's given by, I'll call it L sub curly y, it's just the tensor of all of the determinants of these filtration pieces. Okay, so like I said, this has a definite curvature form already. That makes sense here in Griffiths transverse direction. Is this ample? Is it algebraic? And if it's algebraic, is it ample?
I guess the multiplication of sine.
Sorry?
A plus of -1 over dual or even or the tensor product would just be dv, which is locally constant.
It's each filtration piece.
Yes.
It's not degraded.
Oh, it's
It's not the gradient.
Oh,
Yeah.
sorry.
No, yeah. I'm taking the tensor of all of the
I
filtration.
think this one is very good.
Yeah. Each one of these is in fact, I was about to say, each one of these is semi-positive. You sort of tensor them all together, you get something that's actually definite, and then that's what you expect. And then finally, C, sort of, is there a version of this Baily Borel compactification? Is there a curly y BB? Okay. Okay, so A and B.
And what does C mean? I mean, y is already compact.
Sorry?
Y.
Y is not compact. No, this is the closure inside of here. Yeah. Not compact. And so then, I mean, just like in the two kind of extremal columns of boards, yeah, you sort of close it up in the period domain. There's still boundary yet to be added. And you want to know that there's some kind of version. I'm being a little vague here, but I'm about to state exactly what is true. So A and B were proven a number of years ago with Jacob and Johan Brunebar. And basically the statement is sort of, yeah, all the data you have here in this leg of the diagram is algebraic. Let me just write it like this. So you have this map to curly y, and there's a line bundle. So you have that data. That data is the analytification of corresponding sort of algebraic data. And moreover, that line bundle, Ly, is ample. Okay, great. Okay, so the theorem I want to talk about, like I said, this was a number of years ago, and the theorem I want to talk about today is a solution to question C. So this is theorem 1. Step Mirko, Jacob, I'm just going to change you to a T from now on. Okay, well, hopefully I can fit it all here. I'll erase some stuff. So the first statement is, well, we want to form some graded ring. We call it BY. And this is, well, it wants to be sort of, you sum together the sections. So now we know what this image is algebraic. We can look at sort of powers of this algebraic bundle and look at sections. Obviously, this might be massive because Y is not proper. So you want to sort of take sections that have whose Hodge norm has subpolynomial growth with respect to the Hodge metric. So that's what MG means, moderate growth. Okay, so now this graded ring is finitely generated. And if you take its proj, you get a compactification which satisfies the properties you would want it to satisfy. And so we'll call that the Baily Borel. It is a projective compactification. Of Y. For which the natural line bundle, L sub y, this Griffiths bundle, extends amply and universally in this sense.
And you have to prove that B is time in degree 1 or degree 2 or in a finite degree in order to obtain a projective compactification.
Oh, sorry, this is part of the statement that it gives you a projective compactification.
It's a theorem.
Yeah, no, I'm not saying just, I mean, it could be, just C a priori, but yeah, I mean, it's part of the statement. Is a compactification of Y, for which, I mean, that's, the finite generation is just to make proj make sense. For which, Ly extends amply, and I don't want to write it all out again, but universally, as in 5. Let me just say in words, what does that mean? That's why I left it here on the board. It means in the log smooth situation, whenever you have a variation of Hodge structures on the complement of D, for which the period map factors through the period image of the one you have, so factors through Y, then the map completes to a map to this compactification, and in such a way that this extension of the line bundle agrees with the Hodge theoretic extension. Okay, so it's compatible with respect to the prime. And in fact, even the stronger thing is true, this 5 prime. Okay, great. So let me make a couple of remarks. I'm leaving up these boards because I kind of want to tick off all the properties I mentioned, and hopefully they'll agree with the properties we proved. So let's see. So here are some remarks. We're already giving this Baily Borel compactification as proj of a sort of ring of a certain line, of sections of a certain line bundle. So that sort of is like this property 2. By stipulation, it has this universal property. And in fact, the stronger version is true. And well, I mean, it has the natural polarization by construction. Okay, so what about these sort of this sort of interpretation of the boundary you're adding in terms of kind of smaller Hodge structures, or in this case, abelian varieties, or this kind of modular interpretation? And the answer is there is a version of that. So this Baily Borel stratification, this Baily Borel compactification is stratified by varieties with quasi-finite period maps. Okay, so up to sort of finite ambiguity, they're almost sort of images of period maps. So that's as close as one can get to this. What period maps are there? Well, they're the ones that are sort of analogous to this moduli interpretation, namely the ones associated to the associated graded of the limit mixed Hodge structure, which I'm not going to get into the details. Namely, those of the associated graded. Okay, so that's the first remark. Second remark is that there's been some previous work on this question of producing Baily Borel compactification. So in particular, previous work of Griffiths, Robles, and Laza. And also a follow-up paper by Green, Griffiths, and Robles. Which do some special cases. In particular, they do the case where the base is two-dimensional. And also sort of they prove what will be an important ingredient in the proof I'm going to try to sketch. So the second paper, so GGR proves important ingredient. I think now I can safely start erasing these.
I have a question. If you have a family over X of a subline, you restrict it to a subspace of X, then you can do the construction for X and for the subspace.
Exactly.
You have an embedding when you take this Baily Borel.
So up to normalizations, you will have a map, yeah. So somehow if you imagine, you can do the same thing in AG, you can imagine something that sort of has a node at the boundary and sort of this will kind of separate out those two branches. Or more generally, you might have some kind of analytic structure that is non-semi-normal. And basically, we make it precise in the paper, but sort of up to normalization at the boundary, because this is actually giving you a compactification of the honest image of the period map, not just the normalization. But yeah, up to sort of relative normalization in some sense that we make precise. That is true. Great. Okay. And then the last remark is in particular, sort of in this log smooth situation. So if you have a variation of Hodge structures on a log smooth, on the complement of a log smooth divisor, you have this natural Hodge theoretic extension of the line bundle, which is, a posteriori pulled back from this compactification on which it's ample. So you're concluding that Hodge theoretic extension of the Griffiths bundle is semi-ample. So sort of LX is semi-ample, which is a statement you can just make in reference to sort of any variation of Hodge structure, in the log smooth situation. Again, this is up to a power because of, quasi and quasi-unipolar.
Like semi-ample doesn't see the poles.
Well, no, but the extension sees the power. If you take the Hodge theoretic extension.
There is a power which extends to some.
Exactly, yes, that's right.
You were only interested in the analytic or the topological thing that you build. Is there a corresponding enlargement of D mod gamma?
Great question. And in fact, that's in some sense, so Griffiths kind of formulates two ways of attacking this question C. And one is by sort of trying to compactify D mod gamma in sort of Griffiths transverse directions and then closing it up there. And the other is sort of via doing this kind of thing. I think more attention has been devoted to the former historically. It's not clear. There's some work of Kato and Usui of sort of doing this in the log category, which would give you sort of a toroidal compactification if you can prove that some kind of combinatorial data exists, but it's not known in general. So the answer is basically you can produce some things for which maybe that's true, but it's not provably true. Although there is some upcoming work of Robles and postdoc and maybe also Jacob. But yeah. What is it? Sorry, what is it? Dang, yes, Robles, Dang, and Tsimerman that sort of address this issue of when you can produce, again, it'll produce something that's more like a toroidal compactification, but when you can produce such a thing, maybe from some partial compactification of D mod.
Would such toroidal thing resolve the problem with normalization if you?
I don't think so. I think that might also be sort of up to this normalization business of the boundary, but I'm not sure. Great. Okay. So in view of this remark, well, one time, this semi-ampleness, there's sort of here's a warning that we shouldn't get too greedy. I mean, I mentioned that each of these determinants is semi-positive. So you could ask if each of them is semi-ample, okay? Each determinant FPV is semi-positive.
Those 45, right?
Yes. Yeah, no, I'm even with that, I'm still running all the time. But thank you. No, if it were half past, then we'd all be in trouble. Well, I'd be in trouble. Okay, anyway, so these are all semi-positive. You could ask if they're semi-ample. They aren't all semi-ample in general. Aren't semi-ample. So it would be nice to have a criterion that tells you sort of when it is semi-ample. And that's theorem 2. Theorem 2 with the same authors. Sorry, I'm and I'll state it in what looks like a special case, but it's actually not a special case. So suppose, let's again talk about it in the log smooth situation. So this is log smooth. And let's say it's proper too. And suppose W comma F dot of W is a Calabi Yau variation of Hodge structures. A lot of letters. So what does that mean? So that means that this is a variation of Hodge structures for which the deepest part of the Hodge filtration is a line. Okay, so i.e. deepest filtration piece is a line bundle, which we call the Hodge bundle. So we call it N. So it's not like that, it's equals Hodge bundle. Okay, so in particular, if the deepest part of the Hodge bundle is a line bundle, then sort of doing the determinant does nothing, so it's semi-positive. And the statement is that the natural sort of Hodge theoretic extension of this line bundle is semi-ample. If and only if two conditions are satisfied. If it is one, integrable, I'll define both of these in a second, and two, has torsion combinatorial moduli. Torsion combinatorial, hang on, I'll spell it out. Combinatorial monodromy. Okay, great. So I guess I can safely let me first make some remarks and then I'll tell you what these two conditions mean. So like I said, this looks like a special case where we're considering a certain case where the determinant is not necessary for the first piece of the Hodge filtration, but sort of variations of Hodge structures form a sort of tensor category. So I can always, for any variation of Hodge structure V, I can always take the wedge to any power and it's still a variation of Hodge structures. So in particular, I can take the wedge to the rank FPV power for any P. And this is now a Calabi Yau variation of Hodge structure whose deepest piece is just the determinant of FP. Somehow the Hodge bundle of this Calabi Yau variation is just the determinant of the FP part of the original thing. Okay, so this theorem really is addressing kind of this question. And actually, it's secretly addressing the semi-ampleness part of this theorem, because there's a similar trick I can play. If I take the tensor of all of these over all P, that's also a variation of Hodge structure, a Calabi Yau variation of Hodge structure, and its deepest filtration piece is just the tensor of all of the determinants. So the Hodge bundle of this is the Griffiths bundle. So again, as far as the semi-ampleness question of this Griffiths bundle is concerned, you can package it into this theorem too, and that's indeed how the proof proceeds. Okay, so as promised, now let me tell you what these two conditions are. So first is this integrability condition. So we say that the Hodge bundle is integrable if for any analytic germ, I don't know, call it G, in X, okay? Well, it should be some kind of integrability statement if this is named correctly. So this is it. You can look at mx restricted to t. So mx lives inside of a flat vector bundle. So you can ask whether it's flat. Okay, so the condition is that whenever there's an analytic germ along which this is flat, it's also flat along the Zariski closure. Okay, so this is one way to state this condition. The other way to state this condition is somehow, from the coefficients perspective, if the Hodge bundle is flat along T or along T, then there's some Q variation of Hodge structure, which is also isotrivial along T. Okay, and those are the same. So that latter way of saying it makes clear that this is automatic for the Griffiths bundle. Because if the Griffiths bundle is flat, then every filtration piece is flat. So actually the whole variation is isotrivial, and the whole variation is isotrivial only along algebraic subvarieties because of the algebraicity of the period. Or even knew that previously.
So what is flat meaning? You mean it's stabilized by the connection of the variation?
Yeah. So this sits inside of a flat vector bundle.
No, a flat bundle. You mean it sits inside of the flat bundle? Is that what you mean, or is it some?
Yeah, I mean, so mx naturally sits inside of a flat vector bundle.
And you mean it's stabilized by this one connection?
Exactly.
And then you said that that is the case, then
it's flat on the Zariski closure of T. So T is just some analytic germ. So the condition, you're assuming that that line bundle is flat along that germ. And then the condition says that whenever that's true, it should also be flat along the Zariski closure of that germ.
So you mean when Griffiths transversality is just when you mean the Konrad-Spencer class on T is trivial, then it's trivial on the Zariski closure?
Yes, correct, yes.
The Konrad-Spencer class is algebraic. So
well, this is in the general, this is for any Calabi Yau variation of Hodge structures, not coming from geometry or anything. This is Calabi Yau in the abstract sense, that just the deepest part is the one.
Konrad-Spencer class I mean, it's abstracted as
no, but it's not. I mean, you could just take some variation that's Calabi Yau and just add some other piece that's varying, and if you take that whole variation.
No, but I apologize. I mean, I don't want to block the lecture, but I mean, to say that it's flat on T means the Konrad-Spencer class dies.
Yes.
On T, so that means the connection respects the infiltration.
Yes.
But I mean,
just of this deepest part.
Pardon me?
Just of the deepest part. Just of this deepest part of the filtration.
Yes.
Is flat.
Yes.
Let me give you an example that maybe is clarifying. Do you imagine a Hilbert module?
One second. Because I mean, Fujita analyzed all that years ago. So then now you take the Zariski closure.
Yes.
If it's true on do you have maybe do you
It's not geometric. Like there's no
Omega could get bigger.
yeah.
Omega could get bigger. T could be an analytic curve, but the Zariski closure would be much bigger. So omega is bigger.
Yeah.
But do you have an example where on a germ, analytic germ, it is on an analytic subvariety?
Yeah, so you take a Hilbert modular surface, which has a transcendental foliation along which 2 bits of the Hodge structure over R is flat. You can kind of shift things around, but that only one of those is the Hodge bundle in this sense. So it's flat along these transcendental curves, but not along the Zariski closure because there's Zariski density. So that's the kind of thing that can happen. Yeah, okay. But this cannot happen. So as related to what you're suggesting, this is automatic for the Griffiths bundle because the Griffiths bundle records the whole filtration. So the whole filtration is flat, and the whole variation is a trivial for Griffiths bundle. Okay, and the second, let me go over here. Yes, what is this? Second condition is maybe what you would expect. Torsion combinatorial monodromy says that, so MX has, say, torsion combinatorial monodromy. If whenever you have a connected curve along which this Hodge bundle is numerically trivial, then it's torsion. If for any connected curve,
No curve is algebraic.
yes, algebraic curve.
Fujita is precisely 6 point here. That's the one, I made a mistake. Fujita is precisely what you spend now.
Ah, okay, but it doesn't, okay, well, for reasons, it does not imply the statement I'm about to write.
No.
Oh, you're saying over here, this kind of business for this positivity for.
Now I understood what you said something, but here this condition was developed by Fujita.
For any connected C, if this line bundle restricted to C is numerically trivial, then it's torsion. Then it's restricted to C. Okay, so this somehow means, you should imagine some kind of loop of curves. And this Hodge bundle is degree 0 on each component, which Hodge theory then tells you it's torsion on each component. But it does not tell you that the monodromy around this loop is torsion, and that's why it's called combinatorial monodromy. And the condition is that whenever this situation arises, that it is the case that it's torsion. Okay? So like I said, this condition is not always true. And in fact, you can also kind of use the Hilbert modular surface to kind of cook up an example where it's false, because kind of the cusps look like rings of curves exactly like that. And you can get sort of multiplication by real units showing up in the monodromy here. But there's an important setting in which it is true. It's sort of where the Calabi Yau variation of Hodge structure comes from. So that's theorem 3. So I'll say this a little informally, the Hodge bundle of the middle cohomology of a family of Calabi Yau varieties. In fact, more generally, of sort of KLT log Calabi Yaus. This is kind of the geometric circumstance, that motivates the introduction of this definition, satisfies those two conditions. Satisfies star and double star. Okay, so in particular, via theorem 2, that means that it's the Hodge bundles. Some powers. Okay, and this is what allows you to deduce this b-semiampleness conjecture, which is a semiampleness statement for a certain line bundle appearing in sort of families of possibly quite singular Calabi Yaus, which is why it's sort of connected to this. So I won't say precisely what it means. This is what implies b-semiampleness conjecture of Prokhorov Shokurov, which is sort of an important statement in birational geometry. And I'll kind of tell you the kind of statement it is. You may be familiar with the sort of Kodaira canonical bundle formula for elliptic fibrations. If you have an elliptic fibration, so a surface that's generically fibered in elliptic curves and maybe some singularities, maybe even some more complicated singularities arise. Okay, so this is like a z over x. So the Kodaira canonical bundle formula tells you that sort of the canonical bundle of z simultaneously sort of controls 3 things. So the fact that it's a generic abelian fibration means that the canonical bundle is pulled back from the base, and it's pulled back from, the thing on the base has a natural splitting into 3 pieces, where this is the canonical bundle of the base. So this is sort of controlling that. This is what's called the boundary. It's sort of telling you something about the singularities of the singular fibers. Okay, so the sort of the weight that this attaches to a particular point is related to how bad the singularity is. Okay, so the canonical bundle upstairs sort of controlling the total number of singularities and the total badness. And then mx, which is the moduli part, is sort of the Hodge bundle of the variation of Hodge structures. That's the degree of the map to the J line. Okay, so the canonical bundle upstairs is also controlling that degree. And so there is a version of this in higher dimensions called the canonical bundle formula. Due to the work of many people. I'm not going to write them because there's too many, but I'll just mention them. So it goes back to Kodaira, but Kawamata, Fujino, Mauri, Kollar, and Ambro, at the very least. And so the b-semiampleness conjecture says that in this decomposition that you have, whenever you have sort of a family of KLT log Calabi Yaus, the moduli part is semiampleness, actually, if you go to a good enough model. And so that's what's given by theorem 2 together with theorem 3. Okay. So that's all I'll say about b-semiampleness. Let me also say there's sort of past work in this direction by Ambro himself, and also by Lazich for this. Okay, so in the time remaining, I do want to talk about the some elements, some ideas from the proof. Okay, so and what I want to sketch some ideas from is sort of this proof of theorem 2. So how do you get this semi-ampleness statement assuming these two conditions? Because like I said, that, you know, for as far as theorem 1 is concerned, the semi-ampleness part of it gets encoded into it via this construction. Okay, so ideas from proof of theorem 2. Okay, so semi-ampleness is hard because of the semi. It's much easier to prove that a line bundle is ample because we have, for instance, numerical criteria to prove ampleness by like Nakai-Moishe zone. So the strategy often to prove semi-ampleness is to construct the map that the proj of the line bundle if it were semi-ample. In other words, you want to show that there's a map to some algebraic variety such that the line bundle is pulled back from there and the line bundle on that target is ample. Okay? It's easier to check ampleness. Okay, so that's the strategy here. So step 1 is to produce that target variety as a topological space. Okay, so make the topological space. Q, so X maps to, I'll call it Q, a quotient. Now we somehow know what this Q has to be. It has to be the quotient of X by the equivalence relation, which just connects, which contracts all points that are connectable by chains of curves along which the Hodge bundle is degree 0. Okay, so R equals being is the equivalence relation being connected by chains of sort of Hodge degree 0 curves. Okay. Now, this construction appears in many places in algebraic geometry. It's not necessarily clear that this is a well-behaved equivalence relation. So the first step is to show that this equivalence relation is in fact a proper algebraic equivalence relation. But at the very least, that means that this X mod R sort of is a nice Hausdorff topological space. And with a little more work, you can squeeze a little more out of this up to, so remember X comma D is sort of log smooth, up to some log smooth modifications. I mean, there's always a natural sort of stratification of a log smooth thing, just given by taking intersections of these boundary divisors. And you want this quotient map to sort of behave well with respect to that stratification, meaning the sort of stratification descends. Okay, more can assume the stratification descends. Okay, let's call the strata, I don't know, Q sub S. S is just a formal symbol. Okay. If I've done this correctly, all the theorems are still on the board. Good. So a key point is that this older theorem with Brunebarb tells you that sort of at least on strata, all of these strata are algebraic because they're all sort of images of period maps, and the line bundle on each stratum is ample. Okay, so each QS is algebraic, and sort of MX ample is algebraic and ample on QS. Okay, so somehow the remaining step to do is this gluing of all this sort of data with respect to stratification, which is the hardest part in sort of Baily Borel's original paper. Let me just draw. Sure. So we have X, it's this, and we have this Q. And I've said the stratification descends, so let's assume the sort of stratification down here looks like, you know, has this piece and then this smaller dimensional piece. So in general, let me say, I don't know, Q less than or equal to I is the union of the codimension I strata. Okay, so the open part is Q0. I'm going to say this is Q1, although that's kind of a lie because usually, I mean, Baily Borel, we know that the dimension of the strata drops quite a bit. So this might be like Q10 or something, but I'm just going to call it Q1 for now. And then this deeper one is Q2. Okay, and the inverse images of all those strata are strata upstairs. So maybe X looks like you have sort of this divisor. And let's just say that sort of the open part is X naught. And then the inverse image of Q1, let's say is this X1. And the inverse image of Q2 is this bit, which is X2. Okay, so what is the name of the game? You want to locally on Q produce sections of the line bundle upstairs that separate fibers, right? That's how we build kind of an analytic space structure here. So like maybe in an open set like that, the inverse image is like this kind of cylinder, and you want to produce sections of the line bundle up here that separate fibers above 2 points. Or I guess the way I've drawn it for this. Okay. So hopefully in 5 minutes I can say a few words about. I'm going to do so by not saying anything about one of the important steps, which is step 2. So this is where kind of this is the part of the proof that makes the most, I mean, the whole thing uses Hodge theory, but somehow the most nuanced Hodge theory occurs in step 2. You locally make sections, some sections of this line bundle MX. So let me say it precisely. Locally on QI, okay, so on any particular stratum, but locally like in the big space Q, so locally along QI, maybe I should say along, locally along QI, make sections in the inverse image of MX separating points on like fibers above points, separating fibers above QI. Okay, so this is sort of the most you can do just with Hodge theory. I guess okay, so I'm not going to say anything about how to do this, but you do that. So that seems pretty good. So why are we done? We've made a lot of kind of local sections. Well, I claim that it's not even enough to produce the structure of an analytic variety on Q. Okay, so actually, I'm going to put that over here. This is kind of an important point, and we're going to try to illustrate it with pictures. So here are 4 scenarios. These are all pictures of Q. They all have this stratification. Okay, and what are some scenarios I might be interested in? Well, on a small open set that doesn't go anywhere near the boundary, I can separate fibers above 2 points. Okay, so that falls under this. And in a neighborhood sort of locally on Q1, I can separate fibers that are on that strata. Okay, so both of these are good. What I can't do is sort of locally on Q1, I can't separate fibers off of the stratum, because that might entail, I mean, all I have from step 2 is I know that if I sort of further zoom in to here, you can find such sections. But there might be a pretty big gap there, because we know that the topology, like locally around the boundary in the Baily Borel, is extremely complicated. Somehow the hard part is showing that you can find those sections kind of all the way around the local neighborhood of this boundary stratum. Okay, so how do we?
There's one more scenario.
Sorry,
There's one more scenario.
there is one more scenario. Leave that as a mystery. No, I'll come back to that. Okay, so final step is step 3. Sort of algebraize these unions of successively smaller strata inductively. Okay, and so what is the point here? Well, the point is this theorem that I haven't erased, good, with the Brunebarb, it's telling you ampleness of the line bundle, sort of, I already said it over here. The line bundle is ample on each of these strata, okay? So I can do better than step 2. Just tells me locally I can find sections that separate, because on the biggest stratum, I know that I can find algebraic sections of MX, which are defined on the whole thing, okay? And sort of somehow Zariski open sets where sections are separated by those sections are way bigger than the analytic open sets that are guaranteed here, okay? So in particular, this is not a problem, right? Because I can find sections, global sections of MX which separate points off of the stratum, and in particular, a global algebraic section is defined in restriction to this this complicated nature. Okay, so this is actually good using the sort of ampleness. And so this theorem with Brunebarb says that in fact there are global sections of MX separating fibers above Q0. Okay, sorry, I'm going to take 1 minute more. I apologize. So that actually is enough to make an analytic structure where I just add in the biggest part of the boundary. Okay, therefore, Q less than or equal to 1 is an analytic variety. Okay, well, I said I wanted to say more about omnimality, but that was, I guess, a little bit of a lie. So the important point here is that this is the definable analytic variety, because all of these sections sort of come from Hodge theory. And then by O minimal GAGA, it's also proven in the same paper, that implies that this is actually algebraic. And even better, the same paper implies that the line bundle, this MX, which now lives here, is ample on here. So why does that make your life better? Well, this last scenario that I didn't mention is even after this step, I still have a problem with this scenario. Sort of in a neighborhood of Q2, I want to separate points above a fiber in sort of a bigger stratum. And this I don't know how to do up until this point. Okay, but once you algebraize Q less than or equal to 1 and upgrade to the ampleness of MX on Q less than or equal to 1, it's more than the ampleness. It's that the global sections on X separate points along Q less than or equal to 1. So in particular, now I have global sections which separate points on Q less than or equal to 1, which includes this scenario. Okay, so now I can run this loop, because now I can add in the next biggest stratum, q less than or equal to 2. That's a definable analytic variety. I algebraize it using a minimal GAGA, blah, blah, blah. And you just keep going. And then by induction, you win. So then induct. Okay. So let me stop there. Sorry for that.
Any questions for Ben?
Can I open a melody, the black box to your work with Brunabon?
So you certainly need O minimal GAGA.
Yeah.
And so the theorem that implies that you need is that the definable analytic image of an algebraic thing under a proper map is algebraic. And that's literally what's showing up here. And so for this part of the argument, yes, you do need that these are kind of definable. So you need to know something about sort of Hodge theory living within the world of O minimal. Yes. Yeah.
Can you say something about like this combinatorial finite monodromy? Like how do you check it in practice? Like,
Yeah, sure. So do you want so which answer do you want? Do you want the answer Y, the Griffiths bundle is always, or do you want the geometric argument for Y for Calabi Yau?
Yeah, what's the second?
The second one. Oh, great. Yeah, that's the one I never get to explain, which is really cool. Yeah, so the point of the middle cohomology of sort of families of Calabi Yaus is there's a geometric part of a nice enough degeneration, which kind of records the like transcendental part of the limit mixed Hodge structure, sort of the smallest subquotient that the Hodge bundle lands in, okay? And so you can kind of geometrically track the sort of part of the Hodge structure whose period map is giving you that stratum at the compactification. Okay, so let me draw this picture. So this is two curves meeting at a node, okay? And so if you look at the degeneration you get along here, maybe it kind of looks like this, okay? And maybe along here it kind of looks like this. And this piece of the degeneration that's carrying that kind of that minimal subquotient of the variation is say maybe here along here and here along here. Okay. Now the issue is somehow when you degenerate further, you know, there's a non-uniqueness here. There are many of these. They're called minimal LC centers. So when you degenerate, you get kind of a picture like this. Okay. So the limit here is like this, and the limit here is like this. And what you need to know is that the map, you know, the identification between the Hodge bundle here and the Hodge bundle here, so let's call this like S1 and S2, you need to know something about, you know, top forms on S1 versus top forms on S2, okay? And here you use a result of Kollar, which tells you that it's called P1 linking. There's somehow sort of these can be connected by components which are ruled by P1s. And the upshot of that is this map that identifies these two is via a birational map from S1 to 2, to S2. It's from birational. Okay, so any birational map induces a, any birational automorphism induces a torsion automorphism in H0 omega, and that's for the tokens.
Let's perhaps postpone other questions to after the talk. Thank Ben again for a great talk.